Welcome to semester 2 and the first tutorial, or also known as tutorial 12. And we're going to start on complex numbers. And this is going to be the introduction. You might remember that I tried to get to polar coordinates at the end of last semester, but we didn't quite get there. So as a motivation, let's just say that a complex number is a polar coordinate. I put that in quotation marks. So let's give a proper definition, remind you what a polar coordinate is. So definition, a complex number z is a polar coordinate r theta p. Let me actually draw the picture without delay. So here's our polar coordinates, x and y axis, and a point z. It has a size r and a certain angle theta. More specifically, so r should be positive or non-negative. It can be 0. And the angle lies between minus pi and pi. So theta, the angle is defined up to 2 pi. We call r the modulus, and we call theta the argument. I mean, alternatively, I would just call this the size, and this is the angle. This polar coordinate representation, so this type of representation of a complex number, this is known as the Argonne diagram. Argonne was a French mathematician, and this is just the diagrammatic representation of a complex number. So that's one particular complex number z. If you take all of them, so the collection of all such z z's forms the complex numbers which is written C with a bold, just like real numbers are written with a bold. But the complex numbers has some additional algebraic structure. So as a comparison, the real numbers aren't just points on a real line, they have further algebraic structure, which I will remind you. So if you think of a real number, so there's a straight line, there's maybe 0, and you have some real number x. It's got some size. There's the size of x. It could be positive or negative. So R has addition, So let's say x plus y. So let's take two real numbers. And what is addition to x plus y? It's going along by x and coming back by y. So you go along by x, and this gives you the composition x plus y, which is this amount. You can think about x plus y. What have we really done? We've gone from 0 to x, and then we've gone back by y. So x plus y as an algebraic structure can be thought of zero plus x plus y. And in fact, I could have added y first and then added x. So if I use dotted line for here, I could have gone to y, then plus x. And this total sum still gives me x plus y, but this time it's y plus x. So what we've actually shown, just to remind you that we've given a geometric description of x plus y is equal to y plus x. So this is thinking about addition in terms of translations. So R also has multiplication. X times y. So by exactly the same arguments, x times y can be thought about as 1 times x times y. And is also equal to y times x. So for the purposes, I suppose I should add that there's a 1 there as well. So the real numbers has addition and multiplication. And so therefore the algebraic structure for the complex numbers, let me start a new page. There's also addition, which is still translation, but now in 2 dimensions. And there is also multiplication as well. But instead of just rescaling, which is the case in real numbers, here is a combination of rescaling and rotation. And that makes sense, because if you remember, if I write z is equal to its modulus and its argument, there's the possible rescaling and there's the possible rotation. So let's just give another geometric description of what I mean by addition and multiplication now in C. So here's the Argonne diagram again. So there's 0, there's 1. This is known as the real axis. Here's the imaginary axis. And if here's my vector or complex number z, you can think about this position z itself as addition of z from 0, the addition of this vector from 0. But maybe it's clearer if I give you another vector w, and we compare what z plus w equals. So we add the vector w onto the position z. So we pretend we start from this point instead of starting from the origin. So here's z plus w. And the combined vector, the new complex number, is this whole vector, the one in green. There's z plus w. I should make this green. And again, but you can see that this is the same thing as the other side of the parallelogram if I add z to w. So again, we've shown that z plus w is w plus z. So that's addition on the complex numbers. What about multiplication? Let me use the same vectors again. So I can cheat and copy and paste. Oh. Bear with me. But this time maybe I will forget about a few of these. Okay, so we have z and w. Z with size r. Oh, I should. And angle theta. And so what is multiplication of w by z? Let's call it wz. That's going to be, I'm going to rescale w by the size of r. The size of z, which is r. That gives us, let's say that r is almost twice the size of 1. So here's something like this is r times w. And then I'm going to rotate by the angle theta. So by the angle of z. So I'm going to rotate all of this by about theta. So you know my drawing is only reasonable. It's something like this. And this new vector here, here's the output, wz. And so maybe it's an exercise or to think about why wz is actually equal to zw as well. Zw would be rotating z by this, multiplying z by the size of w, so it gets up to about here, and then adding on the angle of w, so whoa, you add it all the way up to over here. Here's the general definition, so that's motivation, so let's do the definition of multiplication. So if I give you two arbitrary complex numbers, zi equals ri, comma theta I, p for I equals 1 or 2, z1 times z2 is equal to r1 theta 1 p times r2 theta 2 p, and is equal to, you multiply the sizes, and you add the angles. And this is up to 2 pi. And so you can see, because regular addition and regular multiplication commutes, that's theta 1 plus theta 2 is theta 2 plus theta 1, and r1 times r2 is r2 times r1, we see that this is immediately z2 times z1 as well, as we showed in the picture. Finally, if you're watching this, you can take a deep breath. The alternative definition of complex numbers is when you identify polar and Cartesian coordinates, so that's rectilinear, usual xy coordinates, we obtain that z is equal to r comma theta p is the same thing as, let me draw the picture again. So there's z, where you have its x coordinate, which is r cos theta, and you have its y coordinate, r sine theta. But we're going to write it in a slightly funny way. Here's the real axis, there's the imaginary axis. We review the complex number as r cos theta plus I r sine theta, which is what we traditionally write as x plus iy. And why do we have the I here? Well, this is because the complex number I is rotation by 90 degrees while multiplying by 1. This I is equal to 1 comma pi by 2 p. You multiply it by size 1, so you don't change the size of the complex number, but you rotate everything by 90 degrees, or pi by 2, counterclockwise. So as a final remark, if I do that twice, I multiply the sizes, 1 times 1 is 1, and add the angles, pi plus 2 plus pi by 2 is pi. And that's the same thing as going round, turning your vector wherever it is, and rotating it by 180 degrees, and that just changes the sign. So this is known as -1. So therefore, if you like, I squared is the square root of -1, or one of the two square roots of -1. The other one is rotating clockwise by 90 degrees.